Okay, so today we're covering our test results. The first question is, a scuba tank contains 0.356 kilograms of oxygen in a volume of 2.75 liters. And we're asked two questions. One, to calculate, or A rather, calculate the gas pressure in the tank at 15 degrees Celsius, and B, what pressure is predicted by the van der Waals equation. And they give us the van der Waals equation, and they give you the values of A and B for oxygen, because each gas has its own value. Different gases have different interactions depending on their shape and their size and so on. But anyway, the first step is to calculate it with the ideal gas law, PV equals nRT. We're asked to solve for the pressure. So we rearrange the equation by transposing the V under the nRT, and then we plug in the values. This is how many moles of oxygen we have, and the mass in grams divided by the molar mass in grams, times the gas constant, 0.082057. We use liter atmospheres per Kelvin mole, because those are the units we're using for the rest of the calculation. We add 273.15 to find out the Kelvin temperature. You need to plug in the absolute temperature into the equation to get the correct answer, and then the volume in liters. And we get 95.657, which rounds down to 95.7 because we're only allowed 3 significant figures. Where the mass was reported to 3 significant figures, the volume was reported to 3 significant figures. With the 15, if you put 2 significant figures, I would let it go, because you could argue that's only 2 significant figures, but then we added 273.15, which is 5 significant figures, so you could also argue that this was an exact number. So I'll let it go if you put 2 or 3 significant figures. For part B now, we plug the values into the van der Waals equation. Here's the number of moles of the gas. It's the same as what we get from this calculation. Here's the R value of R, absolute temperature, the volume, minus the number of moles of gas, minus the volume that's lost as a result of the fact that the gas molecules do have an actual volume. And this term helps to take away some pressure as a result of the fact that the gas molecules do have some kind of interaction between each other. So that's what this term is here. We square the value of N, the number of moles, times 1.36, that's the value of A, over the volume squared. We get a considerably lower pressure than what we had in the ideal gas equation. So we see that oxygen does not behave like an ideal gas at high pressure. There's a very considerable difference between the pressures that are exerted under those 2 sets of conditions. In the second question, Frank, you need to move the camera. Number 2, we calculate the density of sulfur hexafluoride gas at 777 torr and 25 degrees Celsius. So, and for B, we calculate the, thank you for that. For B, we calculate we're also asked to calculate the molar mass of a vapor that has a density of 1.315 grams per liter, and to give the temperature and the pressure. So let's do the first part. We use the ideal gas equation, PV equals nRT. We again rearrange for the volume of the gas by transposing the P. We find the molar mass of sulfur hexafluoride. Here's the mass of sulfur. Here's 6 times the mass of fluorine, so it gives us 146 grams per mole. And we assume we assume an amount of 1 mole. Why make life difficult? So by assuming 1 mole, the number here is 1, value of R, the absolute temperature, and here's the pressure in atmospheres. Remember, 1 atmosphere is 760 torr, so the pressure is slightly above 1 atmosphere. And that allows us to calculate the volume of the gas. The gas will occupy 23.93 liters at that pressure and temperature. Then we recall that the definition of density is mass over volume. So we have that there's 146 grams. How did we find that out? Well, we assumed 1 mole, and that's the molar mass of the gas. We also found out that the gas occupies that many liters of volume under these conditions, so we have now what we need to plug into our density equation. This is the symbol for density, by the way, rho. It's the Greek letter rho, that's how you spell it, R-H-O. So the density is equal to mass over volume, and we get a density of 6.1 grams per liter if we only allow ourselves 3 significant figures. And again, we could perhaps argue that this is only 2 significant figures, so if you wrote an answer of 6.1, I won't mark it wrong. In B, we're given the density, so what we're going to do is assume a 1 liter sample to make the calculation easier. So if we assume we have a 1 liter sample and the gas has this density, then we also have 1.351 grams. We take PV equals nRT, rearrange the equation to solve for the number of moles, and we find out that we have that many moles of the gas. We've entered all the, here's the pressure in atmospheres, here's the volume in liters, gas constant, absolute temperature. Then because we know that we have 1.351 grams, and that 1.351 grams is that many moles, we have the basic units for molar mass, which is grams per moles. And we find out that the gas has a 37.9 grams per mole molar mass. If you put 38, I won't mark it wrong, because you could still argue that there were only 2 significant figures because of the 15 degrees Celsius. In the third question, we're asked, at the bottom of a 96-foot deep lake, the total pressure is 4.05 atmospheres. And that pressure at the bottom of the lake is a combination of the pressure of the water plus atmospheric pressure. So if the pressure at the surface of a lake is 1 atmosphere due to the pressure of the ocean of air that we live in, called the atmosphere, which we're at the bottom of, then we know that at least 3.05 atmospheres of the pressure is due to the lake water alone. And roughly 1.0 atmospheres is due to the atmospheric pressure. So at the surface we find out the atmospheric pressure is 1.1. Maybe there's a high pressure zone in the area that day. A gas bubble with a volume of 55.8 millimeters cubed is released at the bottom and rises to the surface. The temperature at the bottom is 4 degrees Celsius. At the surface, it is 15 degrees Celsius. What is the bubble's volume at the surface? So to solve this equation, I only memorize one equation. You know, some people say there's Boyle's law, there's Charles' law. I just memorize the ideal combined gas law, and I cross out anything that I'm not going to use. So there's no mention made of moles in this problem, so I crossed out moles right off the bat. So we only have to worry about P1 V1 over T1 is equal to P2 V2 over T2. I enter in all the values of pressure and volume. You'll notice I use the non-standard, non-SI unit here, millimeters cubed. It doesn't matter as long as I realize that the answer is going to be in that same unit. So you could put any unit in there. You could have pascals, feet cubed, Celsius. Actually, I'm not sure about the Celsius part there because you do need a temperature scale. But I think it might work anyway. The important thing is that you realize that you'll have the same units on the other side. So I rearrange the equation to solve for V2. V2 is over here. So I transpose this to the numerator there, and I transpose that to the denominator. That's where I just wrote the numbers in this part because I was doing the math. And we come up with 258.455 millimeters cubed. We're only allowed 2 significant figures in our answer, so I expressed it as 2 significant figures. This is 0 as the spacer, so 260 millimeters cubed is the volume of our bubble at the surface.